Question number 38. What is the mass of the moon? Probably it's not going to answer whether or not the moon is made of cheese, but I consider that this was something rather interesting and worth sharing. So, I have decided to share this with you, and it says, even if an ancient astronomer were willing to accept Hipparchus' view of the moon and to think of it as a huge world, he might argue that heavenly bodies were composed of pure light and had no substance. Their size might be more important than the size of a cloud or a shadow, for instance. It would be important then to determine the mass of the moon, how much matter it contains, so to speak. But truly, how can you do that? You can't weight it or exert force on it to change its motion any more than you could in the case of the Earth or any object in the Earth. Nor could you go to the moon, at least not until 1969, to measure the pull of gravity on its surface and determine its mass in that way. You could do the following thing. What you could do, though, is to measure the pull of the moon's gravity, assuming it has any on the Earth itself. To work out that answer, let's think about a seesaw. That's seesaw, S-E-E-S-A-W. Something we can all visualize. Imagine a long, flat board pivoted over an axis, with a youngster sitting on either end. One youngster is down, with his feet touching the ground. He kicks so that his end of the board flies up and the other goes down. Then, when the other youngster reaches the ground, he kicks and the motion is reversed. This can be kept up for as long as the youngsters wish. But suppose that one youngster is much heavier than the other. The heavy youngster can kick at his end of the seesaw, which would then go up a bit and come down again, for the weight of the light youngster would not be enough to bring his end down and keep the heavy youngster in the air. The seesaw wouldn't work in that case. The trick would then be to balance the seesaw at a point nearer the heavy youngster. The nearer the pivot is to the heavy youngster, the more difficult it is for him to keep his end down, and the easier it is for the light youngster, far from the pivot, to do so. Finally, a place is found for the pivot that lets each youngster have an equal ability to bring his side down, and the seesaw is back in balance. If you weigh the youngster and measure the distance of each from the pivot when the seesaw is in balance, you will see that the heavy youngster is twice as heavy as the other. The other needs twice the length of seesaw that the heavy one does. In fact, if you know the weight of one youngster but not the other, then if you measure the lengths of the seesaw on each side of the pivot when it is in balance, you can calculate the weight of the other youngster without actually weighting him. This is the principle of the lever, which was first worked out in full mathematical detail in about 250 before Christ by the Greek mathematician Archimedes. That's Archimedes, Archimedes, born in the year 287 and died in the year 212, both of which before Christ. The situation of the Earth and the Moon is something like that of the two youngsters on the seesaw. The Earth's gravity pulls at the Moon so that the Moon revolves around it. The Moon's gravity, however, pulls on the Earth so that there is also a tendency for the Earth to revolve around the Moon. If the Earth and the Moon were exactly equal in mass, then the two tendencies would be equal, and the Earth and the Moon would each revolve about a point halfway between the center of the Earth and the center of the Moon, with each body on the opposite side of the orbit from the other. But if the Earth is more massive than the Moon, the point about which both pivot, the center of gravity, has to be closer to the center of the Earth, just as the pivot of the seesaw has to be closer to the heavy youngster. The Earth is considerably more massive than the Moon, so that the center of gravity is quite close to the center of the Earth. So close that we can simply consider the Moon to be revolving about the Earth and the Earth to be standing still. Nevertheless, the Earth is not standing still. It is making a small circle about the center of gravity each month, and the center of the Earth is always on the side of the center of gravity that is away from the Moon. You can tell the size of the small circle the Earth is making each month by studying the motion of the stars in the course of the months. As the Earth makes a small circle each month, the star seems to make a small circle in the opposite direction. The center of gravity of the Earth-Moon system is 81.3 times as close to the center of the Earth as to the center of the Moon. The center of the Earth-Moon system is about 4,700 kilometers from the center of the Earth. For Americans watching this, that's roughly equals to 2,900 miles. This is 1,600 kilometers below the surface of the Earth. So, you see that it does look as though the Moon does all the revolving. And for the people wondering, that's actually 1,000 miles. I want to make sure that this video is accessible and understandable for pretty much everyone who uses metric system and stuff. That is totally different, of course. Let us continue. This also means that the Moon has a mass that is probably 1 multiplied by 81.3 to the 10th exponent than that of the Earth. That may not sound like much, but it still means that the Moon's mass is probably and roughly 740,000 billion kilograms. That is 12 zeros. Furthermore, because the Moon has a smaller mass, it also has a weaker gravitational pull. You might think that if we were standing on the Moon, we would only have 1/80th part as much weight as we have on Earth. But we must remember that because the Moon is a smaller body, we would be closer to the Moon's center than we are to the Earth's center on Earth's surface. That raises the Moon's surface pull. So, that if we were standing on the Moon, we would have 1/6 the weight we would have on Earth. Once we have the Moon's mass and know its size, we can calculate its density, which turns out to be 3.34 grams per cubic centimeter, only 3/5 that of Earth. From this, we can deduce at once that the Moon doesn't have an iron core as Earth does, but must be rock all the way through. Furthermore, since the Moon is smaller than the Earth, its central temperature is lower than that at the center of the Earth, and since rock doesn't melt as easily as iron does, we are safe in assuming that the Moon does not have a liquid center of any kind. Without a liquid center, there is nothing at the Moon's core that could swirl, or even if there were, the Moon rotates far too slowly to set up those swirls. So, we can conclude that the Moon has no magnetic field. When probes were sent to the Moon to measure its magnetic properties, it was discovered that this was correct. The moon, unlike the Earth, is not a magnet. As for other planets, Mars rotates fairly rapidly, but it too lacks an iron core. Mercury and Venus do have iron cores, but they rotate very slowly. The result is that these worlds are not magnets either. Mercury shows a tiny bit of magnetism, which is rather puzzling.